Welcome everyone. During this lecture we'll introduce two-dimensional position, displacement, velocity, and acceleration. We'll introduce an application of two-dimensional motion. We'll discuss projectile motion. We will introduce the projectile motion equations, and we'll also introduce an application of projectile motion. Let's begin by introducing two-dimensional position, displacement, velocity, and acceleration. Generally, two-dimensional motion may be described as a combination of two independent one-dimensional motions. And those are motion in the x direction and motion in the y direction. So let's draw a Cartesian coordinate system and discuss an object that's moving in two dimensions. Okay, so let's imagine that there's an object crawling on the board along this path that I've drawn. So it's actually moving in two-dimensional space. And we'll also assume that the object starts to travel at this location right here, and it ends its travels at this location right here. We'll call this the initial position and the final position. We indicate the object's location through these vectors. The first one is called r sub I, which indicates the initial position. The second vector is called r sub f, and as you can see, it indicates the object's final position. If we connect the initial to the final locations with a vector, that vector is called the displacement vector, and we use the symbol delta r to define it. So, r sub I describes the object's initial position. And it is a vector, so we'll place an arrow on top of it. Likewise, r sub f describes the object's final position. And delta r defines the object's displacement. And notice that each of these has a magnitude. In other words, there's a length and there's also a direction that's noted by a specific angle. It turns out that the object's displacement, delta r, can be derived by subtracting the initial position from the final position. So delta r just equals rf minus ri, and in order to calculate delta r, we have to use vector analysis techniques. So we'll make a note of that. Let's now define average velocity in two-dimensional space. It turns out that average velocity, which is noted by a v, this line on top indicates average, and in two-dimensional space, average velocity is a vector quantity. It just equals delta r divided by delta t, which can be expanded further as r final minus r initial divided by delta t. And now we'll define average acceleration as well. Average acceleration noted as follows equals just delta v over delta t, and again we can expand that as v final minus v initial divided by delta t. We will now introduce an example that demonstrates these principles. In this example, an object traveling in two-dimensional space is initially located at x initial equals 2 meters and y initial equals 3 meters, and this is of course within a Cartesian coordinate system. After 8 seconds, the object arrives at a location of x final equals 7 and y final equals negative 5 meters. We need to determine the magnitude and direction of the object's initial position, the object's average velocity, and finally, if the object started from rest and attains a velocity of 15 meters per second at an angle of 30 degrees at t equals 8 seconds, we need to determine the magnitude of the object's average acceleration. Let's construct a Cartesian coordinate system, and then we'll indicate the object's initial and final positions. The object starts at 2, 3, which is located right here, and ends at a position of 7, negative 5, which is located right here. And so this vector is labeled as r initial. Again, that's the initial position. And this vector indicates the final position, and we'll label it as r sub f. In part A, we want to determine the magnitude and direction of the object's initial position. And essentially we're looking for r sub I, magnitude and direction. And so what I'll do is I'll isolate r sub I within a small Cartesian coordinate system. This is what r sub I looks like. And of course, if we complete this triangle, the horizontal side is just the x-coordinate, which is 2, and vertically we have 3 meters. Of course, this is the angle that we're associating with that original position. And if we want to find the magnitude of r initial, you could see through Pythagorean's theorem by taking the square root of the x-coordinate squared and the y-coordinate squared, we'll be able to obtain the magnitude. So we have 2 squared plus 3 squared ends up being the square root of 13, and the square root of 13 turns out to equal 3.606 meters. Now we need to determine the angle, And by the way, let's eliminate this arrow on top of r sub I because we're only looking for the magnitude. The arrow on top, of course, signifies the vector itself. R sub I without the arrow just signifies the magnitude. Let's now calculate the angle. First of all, we'll note that the object is located in the first quadrant. And so our first calculation is to determine the inverse tangent of the y component, which is 3, divided by the x component, which is 2. Okay, so we're taking the inverse tangent of 3/2, which equals 56.31 degrees, and so we've completed part A. The initial position can be described as 3.606 meters in magnitude, and the angle equals 56.31 degrees. Of course, the units are meters. Let's take a look at part B. In part B, we want to determine the object's average velocity. So average velocity looks like this, and since it's a vector in two-dimensional space, we'll also note the arrow on top. In our definitions, the average velocity was defined as delta r over delta t, which equals r final minus r initial divided by delta t. And so we have to take a difference of two vectors, and the best way to do that is to construct a chart and then install the components of RF and RI. So here's our chart, and we'll label the columns as x coordinate and y coordinate. Here's RF, here's RI, and of course for RF, let's take a look. The components are 7 on x and -5 on y. And for R initial, the components were 2 on x and 3 on y. And now we need to subtract them. We're not adding, remember, we're subtracting the two vectors because the displacement is defined as R final minus R initial. So let's perform that subtraction. Of course, here we have 7 minus 2, which is 5, and -5 minus 3 equals -8. Turns out that these are the components of the displacement vector. So let's note the fact that the 5 and the -8 are the x and y component of the displacement vector. Now, in order to find the average velocity, we need to determine the magnitude of the displacement vector. And in order to do that, we'll just once again apply the Pythagorean theorem. So in this case, the x component is 5 and the y component is -8. So we'll square the 5, we'll square the -8, and using the calculator, we will obtain 9.434 meters. Next, we want to calculate the angle that's associated with this displacement. The first step is to calculate the inverse tangent of 8/5. And that results in 57.99 degrees. We'll also note that the displacement vector has a positive x component and a negative y component. That means we're in quadrant number 4. And in quadrant number 4, from our adjustment table, theta equals 360 minus the calculator value. That's 360 minus 57.99, and that leaves us with 302 degrees. So now we can write the fact that delta R equals 9.434 meters at an angle of 302 degrees. To calculate average velocity, let's again introduce the relationship, which is delta R over delta T. Now delta R is right here. It equals 9.434. The angle's 302. And the time in part B was 8 seconds. And so the average velocity equals 1.179, and the angle's 302 degrees. And of course, the units for average velocity are meters per second. Let's take a look at part C. In part C, we need to determine the object's average acceleration, assuming that it started from rest and it attained a velocity of 15 meters per second at an angle of 30 degrees at a time of 8 seconds. So we want to find the average acceleration. Now the average acceleration was defined earlier as delta V over delta T, which could be expanded as V final minus V initial divided by delta T. We'll also note that the initial velocity was given as 0. And we know the final velocity. We just found that the final velocity in the example equals 15 at an angle of 30. So all we have to do is to introduce this final velocity. Again, it equals 15. The angle's 30 degrees, and we'll divide that by 8. Very simple operation. And so the average acceleration in this case just equals 1.875. The angle is 30 degrees. And the units for acceleration are meters per second squared. We will now introduce the topic of projectile motion. Projectile motion describes the path, velocity, acceleration, time relationship, and position of an object that travels through two-dimensional space under the exclusive influence of the Earth's gravitational attraction. I want to highlight the word exclusive, which means only the Earth is allowed to exert an influence in order for the object to be considered a projectile. In addition, the following conditions must be satisfied. First of all, the object maintains no contact with any other independent object. Secondly, there's no significant spin. Air drag must be negligible. Also, there are no propulsion mechanisms. Such as propellers, engines, etc. And finally, the object must be located near the surface of the Earth. We will now derive the projectile motion equations. And we'll do so by considering a football that was just punted from ground level, and we'll imagine that the football flies through the air and then eventually returns to ground level. So here's the field, and we'll also include a Cartesian coordinate system, and we'll draw the football like so. And the football was just punted, so it has an initial velocity, and that initial velocity is called v0, and we'll indicate it like this. Now I'm just indicating the magnitude, but we note that the initial velocity is actually a vector quantity. It has a magnitude depending on how hard we kick the ball, and it also has an angle which we'll define as theta. After it's kicked, the ball will follow a path that looks something like this, and then the ball will eventually reach the ground, but we're not allowed to let it touch the ground, so we can draw it just before it reaches the ground at some time in the future. and just before it reaches the ground, that ball will have a velocity, and so we'll indicate that with speed lines. I'm also going to draw the ball at some intermediate location, right here. Of course, the football has a velocity there as well, so we'll indicate the speed lines. And we'll indicate the fact that there is a velocity by introducing v at this location. V notes the final velocity of the football, and without the arrow, we're just indicating the magnitude. Now, throughout its flight, we will separate the ball's characteristics into two separate categories. We are interested in the behavior in the x direction as well as the behavior in the y direction, starting with the ball's position. How do we identify where the ball is? Well, we just use the x and y coordinates as a means of identifying the ball's location. So if we know the x coordinate right here, and we know the y coordinate of the ball across the y-axis, which is right here, knowledge of that information permits us to identify the location of the ball. What about the ball's velocity? We would like to separate the ball's velocity into how rapidly it advances along the x-axis versus its characteristics along the y-axis. In order to do this, we will introduce some sunlight. So there's the sun, and the purpose of this sun is to enable the ball to cast a shadow across the field. So if you can imagine the ball flying through two-dimensional space, under sunny conditions, it would also create a shadow that's running across the field, and that shadow is directly under the ball at all times. Let's represent that horizontal shadow with this dotted football right here. And we'll note that when this ball takes off with an initial velocity VO, the horizontal shadow will also take off with a velocity, but it will not equal VO. It turns out that the initial velocity of the horizontal shadow will equal something that we'll label as VOX. And also, later we'll note that the relationship between VO and VOX is related to the cosine of the angle. And so VOX, we will learn in just a bit, equals the x component of VO. Now my question to you is, if this football is flying through the air, will this shadow start quickly, slow down towards the middle, and then speed up towards the end? Will this shadow start out slowly in the beginning, speed up in the middle, and then slow down towards the end? Or will this shadow just travel across the field with a constant velocity? As it turns out, the football will advance across the field with a constant velocity because there is nothing that's influencing the ball's motion in the x direction. Now, there is something influencing the ball in the y direction, and that is the gravitational attraction of the Earth. But the Earth only influences the ball in a vertical sense, not in a horizontal sense. So if we were to examine the velocity of the horizontal football at all times, we would find that the velocity does not change. So let's draw the horizontal football right underneath of this location. This is the horizontal shadow sometime later. It's still traveling to the right. And we'll label its final velocity as Vx, and note the relationship that we've established. We noted that the final velocity, or any velocity, throughout the flight of this ball for the horizontal shadow will equal the initial velocity. So Vx, there's our first relationship, will just equal Vox. So if this shadow starts off traveling at 50 miles an hour across the field, at this location the shadow will also have a velocity of 50 miles an hour. Now we also need to consider the behavior of the ball's velocity along the y-axis. And so we'll introduce another shadow. And in order to create this y shadow, let's imagine that we're illuminating the y-axis with a high power projector. So this projector is shining a very strong light onto the screen, and because of that, it's creating a shadow in relation to this football. This shadow along the vertical screen will be moving with a velocity that we'll call v0y. And the relationship between v0y and v0 that we'll note in just a bit is v0y is just the y component of v0. So initially, this vertical shadow will be heading upwards. Sometime later, when the ball's over here, since the ball's on its way down, if we just project the ball's location, while this ball's on its way down, its vertical shadow will be headed down as well. So let's draw that on the y-axis, and we'll show that the speed lines are headed downwards. The velocity of this vertical shadow at some time later is just going to be called Vy. Now, the vertical characteristics are not constant. What we'll find out in just a bit is that the vertical shadow has a maximum velocity at the point where the football is initially kicked, and thereafter this vertical football shadow will slow down until the ball reaches its maximum height. Let's see what happens at that location. So here's our football at maximum height. It's still moving, but since it reached maximum height, it's no longer rising and it's not descending, it's only moving to the right. Which means that the vertical shadow is not rising or descending either. If we're observing the vertical shadow at maximum height, which is right here, it would not be moving at all. And since we're noting the vertical shadow's velocity as Vy at maximum height, Vy will equal 0. We'll indicate that this location corresponds to maximum height, and this is a very, very important observation. Vy will equal 0 at maximum height. Let's now formally define all the variables that we just discussed, starting with the definition of x. X was just defining the x-coordinate of the object, and y defines the y-coordinate of the object. So this is the way we locate the object, through its x and y coordinates. V0 is defined as the object's initial velocity. V0x, which is the x component of the object's initial velocity, is defined as the initial horizontal velocity. It's the horizontal shadow's initial velocity. So Vox equals the initial horizontal velocity. And likewise, V0y equals the initial vertical velocity. So if you can imagine that we have this projector that's shining a light on the y-axis, which we're imagining to be a screen, v0y indicates the speed with which the vertical shadow begins its journey. So if the football is kicked, let's say, at 90 miles an hour, it may be that the vertical shadow starts to rise, I don't know, maybe at 60 miles an hour, and the horizontal shadow might be traveling at maybe 50 miles an hour, depending on the angle. Let's now define v, vx, and vy. V is defined as the object's final velocity. Vx is defined as the final horizontal velocity. And Vy is defined as the final vertical velocity. I want to note that final refers to any time after the initial. It doesn't necessarily have to refer to the time when the ball returns to the ground. Any time after the ball is kicked, any position, that position is referred to as the final position, and the velocities at that position are referred to as v, vx, and vy. Let's just review the three of them one more time. So this may be considered the final position of the football, and at that position the velocity is noted as v. At this location, the horizontal shadow is traveling to the right directly underneath of the football. The horizontal shadow's velocity is referred to as vx. We noted that this velocity doesn't change. Whatever the ball started with, that will also be the velocity that it ends with at any particular location. And finally, Vy refers to the velocity of the vertical shadow, which in this case is descending. And so if we are looking at the football at this location, the vertical shadow is descending, and if we calculated Vy, we would expect to obtain a negative value because this football is on its way down. While we're here, let's emphasize one more point, and that is when the football reaches its maximum height, its vertical shadow stops rising and it hasn't begun to fall. Therefore, it's not moving at all, and that's why its velocity is considered to equal 0 at the maximum height. Let's now define the trigonometric relationships for the initial and final velocities. We'll start by drawing the initial velocity vector, which looks like this. If we draw its horizontal and vertical components, we would form a triangle, and the horizontal part of this triangle just equals v0x, and the vertical part equals v0y, and of course this is our initial launch angle. From trigonometry, v0x will just equal v0 times the cosine of theta. Likewise, v0y will equal v0 times the sine of theta. So we're discovering that if the initial velocity is known and the initial launch angle is known, we can use that information to determine the initial velocity of the horizontal shadow as well as the initial velocity of the vertical shadow. And that's very important as we consider various projectile motion problems. One other note, and that is the tangent of this angle just equals the opposite side over the adjacent, which in this case is v0y divided by v0x. And finally, let's apply Pythagorean's theorem to this triangle, and that would produce the fact that v0 just equals the square root of v0x squared plus v0y squared. Now there's a similar triangle that we'll analyze for the final velocity. So let's assume that the final velocity looks like this. If we complete the triangle, the horizontal portion equals v sub x, and the vertical portion equals v sub y, and this may be the angle that's associated with this velocity. From trigonometry, we could see that v sub x will just equal v times the cosine of this angle, and vy will equal v times the sine of this angle. The tangent of theta will equal the opposite over adjacent, which is vy divided by vx. And finally, the Pythagorean theorem reveals that v equals vx squared plus vy squared, square root. So with knowledge of the horizontal shadow's final velocity, as well as the vertical shadow's final velocity, we can actually calculate the final velocity of the object or the football itself. Let's now consider two more horizontal motion equations. As you recall from our diagram, we mentioned that the horizontal shadow starts with a speed of Vox and ends with a speed of Vox. We refer to its final velocity as Vx, and this is the equation, this is the relationship. Vx just equals Vox. Also, we established that Vox equals V0 times cosine theta, and now we will just record that formally. So Vx just equals Vox, which also equals V0 times the cosine of theta. Let's now consider an equation that we established some time ago, and that equation for horizontal motion looks like this. X equals V bar t. This is the x coordinate versus time. For projectiles, the average velocity in the x direction just equals v0x, or it equals vx. Either one will do. So if I make that substitution, the equation that is useful to us is x equals v0x times t. So these are the horizontal motion equations. Let's now discuss vertical motion. Well, an analysis of the vertical shadow's behavior reveals that it behaves just like a freely falling body. So even though this football is a projectile moving in two-dimensional space, if we evaluate the characteristics of the vertical shadow, we find that the vertical shadow behaves just like a freely falling body. So we can now customize the freely falling body equations and adapt them for the vertical shadow. Earlier, we developed the following equation for freely falling bodies. It looks like this. Y equals V0t minus 1/2 gt squared, where V0 refers to the freely falling body's initial velocity. But there's a problem, because for projectiles, V0 refers to the projectile's initial velocity. Only the vertical shadow is considered to be a freely falling body. So what is the vertical shadow's initial velocity? We defined it right here. The vertical shadow takes off with an initial velocity of V0y. And so we'll customize this equation by introducing a y right here. And now we have the equation that we're looking for. So the y coordinate of the ball at any time depends on the initial velocity of the vertical shadow, which is called V0y. Another equation that we developed looks like this. V equals V0 minus GT. We have to customize this for the vertical shadow. So V refers to final velocity. The final velocity of the vertical shadow, let's take a look, it's referred to as V sub Y, not V. V refers to our football. We're only considering the vertical shadow. So we'll customize the V with a little y. Also, V0 has to be connected to the vertical shadow's initial velocity. And if you recall, the vertical shadow's initial velocity was called V0y. So there's our second equation. Vy equals V0y minus GT. Next, we have the following equation. V squared equals V0 squared minus 2GY. Again, if we customize this for the vertical shadow, the final velocity of the vertical shadow was labeled as Vy, and the initial was labeled as Voy. So these are the vertical motion equations. And they describe the vertical shadow's characteristics. So how do these vertical and horizontal characteristics help us to define the football itself? Well, if we want to determine the actual velocity of the object traveling through two-dimensional space, such as, let's say, velocity, we can do so through the Pythagorean theorem. In other words, the ball's actual velocity will just equal the horizontal velocity squared plus the vertical velocity squared. And also, to find the direction of travel for the projectile, in other words, theta associated with that velocity, we will use the procedure described earlier. And just to summarize, that procedure required that we calculate the inverse tangent of the y component divided by the x component. In this case, we're talking about velocity, so it would equal the inverse tangent of v sub y over v sub x. And then step 2 would require that we adjust this value according to the quadrant that v is lying in. These equations require that we always introduce g as positive 9.8 meters per second squared. If we introduced it as a negative, look what would happen. Let's say in this equation, if g was introduced as a negative, the negative would cancel out this negative and yield an improper solution. And so g must be entered in as a positive 9.8, and we must retain this negative. Secondly, all problems must begin at x equals 0 and y equals 0. So in the case of the football, wherever it was launched, that's considered to be 0, 0. However, let's say we're launching a package from an airplane that's 500 meters in the air. The location of the airplane now is 0, 0, and the ground is considered to have a negative y coordinate. Finally, we already emphasized this, but one last time. At maximum height, v sub y equals 0, which means that the vertical shadow has no velocity.